We've seen asteroids come through the atmosphere and kind of explode and cause some damage. And thankfully, so far, nothing recent enough that it really has a large impact on our civilization, but it could happen.
There are multiple different ways that you might attack the problem of, oh no, doomsday asteroid is inbound. One of those ways is a kinetic interceptor, which is what DART is working on.
As part of planetary defense, DART, which stands for Double Asteroid Redirection Test, its mission is to impact an asteroid in a binary system.
The reason we're doing this test is to try and prove out the technologies that would be needed to, say, save Earth if an asteroid were coming our direction and we needed to adjust its trajectory so that it would miss the planet.
SmartNav is the autonomous algorithm on board, and the purpose of SmartNav is to identify Dimorphos, which is the smaller of the two asteroids in the Dimorphos system, and we send maneuver commands to the spacecraft for the spacecraft to hit Dimorphos.
SmartNav, the small body maneuvering autonomous real-time navigation set of algorithms, was developed because as we're getting images in from the spacecraft, there's not enough time for humans to be in that loop, responding, issuing guidance commands up to the spacecraft. So we've developed a set of autonomous algorithms to look at the images that are coming in on the camera, to assess them, to identify what pixels correspond to asteroids, what pixels don't, then to take those asteroids, feed them into a filter that then estimates how far are we actually going to miss the asteroid. We need to correct our trajectory to hit it. And so all of that's going to go on board the spacecraft.
We don't really know exactly what we're going to see when we get there. The way SmartNav operates is it has to essentially derive exactly how it's going to maneuver the spacecraft based purely on what it sees.
Draco is our instrument on board, and so it really is the camera. So if you consider the brain as the SmartNav algorithm, Draco is the eyes that provides the inputs to the SmartNav algorithm.
SmartNav moves the spacecraft from side to side. The guidance and control part makes sure that spacecraft is pointed in the right direction. So, if you're taking a picture with a camera and you don't point it in the right direction, you don't see anything. You don't see anything, SmartNav's not going to be able to work.
There really is this focus on we need to be able to collect data at the very end. And one of the things that interferes with the collection of data is when we do maneuvers. When we maneuver, we shake things and we can get blurry images. Now, from the standpoint of SmartNav, a slightly blurry image is fine. We can still find the center of it. But from the standpoint of trying to track on the asteroid individual craters to help tell the scientists precisely where we hit, that's not going to work. So there's this restriction that about 2 minutes out, we have to stop maneuvering. And we're moving at 6 kilometers a second. So if you actually look at that on the map, it's as if we were over the Indy 500 when we stop maneuvering, and then we simply have to coast all the way to Baltimore. And we have to land inside Camden Yards.
To be successful, we have to show that we actually change the orbit of the secondary asteroid around the primary.
Even though we don't know exactly what Dimorphos will look like, we're confident that we've kind of spanned the simulation space of what that could look like. And in all of those cases, we're confident that we'll be able to close that loop and impact the asteroid that we want to impact.
This will be the first time that a spacecraft does do this autonomous navigation, guidance, and control on board. And it will be the first of many future missions that we are going to put more autonomous behaviors on board a spacecraft. And so for us, this is kind of the first step in that path.